So let's get our notes last. Little bit.
For the videos that they watched on last 2 Fridays ago.
The Friday before the 3-day weekend.
Yeah, the one that you were on.
Yeah.
I just like get the titles of the videos and watch them.
Well, if you can get that video, talk to me after class. All right. So our last little things. Now remember, once you do a lab, once we do our experiment, we have to figure out, and we have all this data, we need to do something with it. Now there are two terms, and how these terms are used in everyday English is different than how we use them in science. Mainly it's that word theory. Theory. Now, when you are, say, having a debate with somebody, and you're having kind of a disagreement with them, they might retort with, well, that's just your theory. And what they mean is, you have an idea, but you have nothing to back it up. In everyday usage, if you were to define what theory meant in everyday usage, they use the definition of hypothesis. Okay? But theory in science is a little more. The hypothesis is that educated guess. It's that thing that has no experiment, nothing to back it up. You have an idea based on some other research, something out there. It's like, okay, I looked at this guy's research, or I looked at some experiment I did, and it seems that I can go someplace else with it. It seems that this could happen. But it's only an educated guess. I have some other things. Most research, if you are going, when they report, they make their paper on it and all that, they would have references to those things. There's very few things in history, in research, that did not have those other works cited. I mean, one of the few I can think of is that guy up on the wall, Albert Einstein. When he came up with these ideas of special relativity, he published those ideas. There were no references. There was no other work. This was his idea completely alone. There was nothing that came before it. I mean, even Isaac Newton said he could see farther because he stood on the shoulders of giants. He was talking about guys like Galileo and Kepler and Tycho Brahe and people like that. But theory. Now, once we've tested this hypothesis over and over and over again, I can now develop it as a theory. Theory is a well-tested hypothesis. So in science, theory is a well-tested. So if you're going to have a theory about something, well, you have a lot backing for it. If I tell you I have a theory, this theory means I have all this experimental data to support what I'm saying on that. Proven true, but maybe not necessarily, it's not universal, not in all situations, or you just haven't been able to test it in all situations on that. Anyone need a little more time on this slide? So, once we really test it, we might develop that theory into a law. And laws are universal truth. You can think of these are the rules for how the universe works. Laws of science are the rules of how the universe is put together and how the universe works. And in fact, in all places at all times. This idea of the universe, the entire universe. And they can never be violated. That's what makes it a law. A lot of these laws that we will see in physics are what we call conservation laws. In other words, whatever was the case in the beginning will be the case at the end and at all other times. This is like rule number 1 of the universe, is the law of conservation of energy. Energy is neither gained nor destroyed, but only changed from one form to another. All the energy that was there in the beginning is the energy that's here now, is the energy it's always going to be. No more, no less. But there are other conservation laws, things like conservation of charge, conservation of momentum, conservation of mass. But there are other laws too. We'll see laws of motion. We have Newton's laws of motion. We have law of universal gravitation. We have Coulomb's law of electrostatic force. We have Kepler's laws of planetary motion. We have Faraday's law of electromagnetic induction. Again, these are the rules of the universe on that. Now, a principle is kind of the same as a law that's very, but we kind of put a box around it. We say, okay, under these conditions, this will always happen. But you specify the conditions, you give it things like that. Now, the thing is, hallmarks of science, things can change. But with evidence. I mean, there has been laws at times and different theories that people thought this is the way things were. But because of technology and stuff or other theories. I mean, time is a constant. When events occur is a constant, no matter what. And we actually, with Einstein, we find that time is not a constant. Time can vary depending on how you're moving. In other words, this event occurs at this time to this person, it occurs at a different time to someone else who is moving, or is it what we call a different frame of reference. So things change. But again, to make things change, that means just because we want it to change, it changes? Or do we have to have an enormous amount of evidence to make that change? Enormous amount of evidence. So that's always a thing to keep in mind on that. Enormous amount of evidence on that. So, first thing is the problem and hypothesis sections. Now, the problem is always what I give you. You should write exactly what the problem I gave you. Though some people don't. I don't know why. The hypothesis has two elements. One, it answers the question. It's the answer to the question. And it has a reason. Any reasonable reason. But it has to be an answer. What it means by that, you're going to see in the rubric. If the problem was, why is the sky blue? And you put as your hypothesis, aardvarks are green. Now I'm using a little hyperbole here, but do those go together? Does aardvarks are green answer in any way, shape, or form this, why is the sky blue? No, they're not even close. So you're supposed to have an answer that is a possible answer for our problem. So look at the person's lab and comment on, did they do that? First of all, did they do that? And if they left out the reason, say, hey, you need a reason here. Your question might not be answering your problem. Really, your hypothesis was one of three possibilities. Either long ones were going to be faster, short ones are going to be faster, or neither one is going to be faster than the other. They're both going to be the same. Those are really your three possibilities here on that. So write that little comment. Now, within this section is also the format point. So you might say, you look at your lab report, it's like, hey, I have the problem, I have the hypothesis, I have a reason, but I still got a 3. Why do I get 3? Well, because you probably missed a formatting thing. One of the most common formatting errors that you would get errors is pronouns. We do not use personal pronouns in this style of writing. I, we, he, she. We try to avoid even it. No personal pronouns. We write this in the third person, gender neutral form. Instead of saying, he dropped the whirligig, you would say something like, the whirligig was dropped. It sounds a little awkward at first, but this is the style of writing. This is why I ever read technical manuals, like instructions. Not only instructions are usually written by somebody who, one, is translating instructions from one language into English. The person who's translating it, probably neither the first language it was written in nor English are their primary language. So it's like saying, okay, these instructions are in Chinese, I'm translating English, but I only speak Hindu, or I only speak, Kurdish, or I only speak this thing. So they're using a third language to translate to. This is why this is a real problem. The other problem with instructions is they're written in this technical writing style. Very third person. I actually took a course in college for this style. This is the style that they write in the Navy. In fact, our class project was to rewrite the operating manual for the new yard patrol boats. When I was at the academy, we started getting our new yard patrol boats, which are the little ships that we used to train with at the academy. We had these old ones that were about 80 feet long. They were built during the Korean War, a long time ago. And in the 80s, they started delivering new ones. They're about 120 feet long, a lot nicer. You know, enclosed bridges, things like that. So we got the job of actually rewriting the little manual that everybody got and how to operate those ships on that kind of training manual. So on this, you'll notice merits 1, 2, 3, 4 on the rubric. Problem, hypothesis are missing would be a 0. Your hypothesis doesn't answer the problem, no reason given, and improper format. So basically, you only have the problem right. Everything else is wrong. 2, the hypothesis answers the problem, but no reason given and improper format. You notice how we're adding detail as we go up? It's like the details are changing. Hypothesis answers the problem, no reason given or improper format. So it's like 3 things wrong, 2 things wrong, 1 thing wrong, everything right. So you can see that's how the rubric is written. It has to do with detail. All right. Then we get to the observations. 1, look at the tables. Do they have headings and units? So they should have wingspan, centimeters, time, seconds. There should be always that. If they don't have that, make a note. You need to add something to the heading. Tables are in the section not attached. You may not attach tables. Tables have to be in the body of that. There are only 2 things that you can attach, and we'll talk about those in a second. Qualitative observations should reflect events that could adversely affect data. That's our main purpose of those qualitative, those little bullet statements. And they're written as little bullet statements, not paragraphs, little bullet statements, little sentences, one after another. Now, full credit is given to qualitative observations tied to a specific quantitative observation. What does that mean? Well, let's say I have a bullet statement, and I say, well, at 2.5 centimeter trial 3. That means that wingspan, the 3rd trial, could not get the whirligig to fall straight. Okay, so I know that on that particular one, maybe it's going out thing because it kept going at an angle. That's something it could adversely affect. But I know this trial, this little box on that data table is what this qualitative observation goes with. It is tied to that particular one. That's what it means by more detail. Now, one of the only 2 things, if we build something, you have to draw that diagram there. That's that last page of the packet, shows you how to do a proper diagram, the top, side, those things. That can be attached to the back. That's one of the only 2 things you can actually attach to a lab report is that diagram on that. So now look at the observations. Are they appropriate? Do they have the appropriate detail in their qualitative? Do they have some qualitative? I mean, you should have some qualitative in the lab. And again, this is 0, 1, 2, 3, and 4. Data is incomplete. You get a 0. In other words, the tables are only half filled. Qualitative only. If you don't have any qualitative or you did not put the data in a chart, you'll get a 1. The most common score is usually most people are at least here at the C level. That means you just have the table. You just have the table, you're going to get that 2. That's that kind of C level. If you have the table and some general qualitative, remember I don't know that this box and this qualitative observation belong together, that's the 3. And the 4 would be that one like I wrote down where I know exactly this box goes with that qualitative. Does that mean every single qualitative observation has to be tied to a box? No, because some aren't going to be. I mean, there could be general ones that about conditions, but usually something's going to occur. Usually we do that to show that this is the point in the lab that something happened. Like if you had to switch timers, or you knocked something off, or something had to be replaced, or you replaced someone in your group. Say someone was timing, and should the same person, if you start with one person time, should they be the person that times throughout? Yeah, say they got pulled out of class and you had to switch timers. Could that throw out your data? Yeah, it could, because not everybody works the stopwatch the same. Okay, especially our trend ones. It's not always vital that we get everything exactly right, but that we have the same general trend. So hopefully if a person is kind of doing something wrong, they're always doing it wrong the same way. So it doesn't alter our data per se. You would be accurate, just not precise. You know, the difference between accurate means like if you were shooting, say you're out shooting bows and arrows, accurate would be like you always hit the same spot on the target, but it's not the bullseye. So you're always up in this part of the target, but you always hit the same spot. That's being accurate. Precise means you're always hitting the bullseye. So there's a difference. You can be accurate, not necessarily precise. All right. So on this, we have that. Next comes our calculations. Now those double 2 times. So all the scores here are doubled on that. And there are really 3 parts to the calculations. One is the table. That calculation table, we put the answers to our math. They're separate from the observation table, 2 different things. 2 is the sample calculations. I did that for you, but you have to do that yourself, sample calculations. 3rd part is the graph. Then we're going to talk a little bit about the graph, but not much, because we'll get to the graphs when we do something that needs to be graphed. There's nothing in this lab that needs to be graphed. Now, graph is the other thing that can be attached. You can attach, because you're going to do it on the computer, you're going to get a printout out of the printer, and you just attach to the back. That's the most common thing you're going to attach to a lab report. But you do have to add some information. We'll show what information you have to add to that. All right. On that. So look at theirs. Did they have another table? Did it have the proper, wingspan in centimeters, average time in seconds? Did they have that proper sample calculation? Now, basically, because it is doubled, that's the points. And how I usually grade, if there is a graph, 4 points is the graph of the 8, 2 points is the table, 2 points are the samples. This is where my point deductions come from. If there's just if there's no graph, then 4 for the table, 4 for the sample calculations. Okay, so that's how it kind of breaks out on the 8. Now, if you're missing 2 of the 3 elements, you get a 0. If 2 or more of the following happens, your graphing missed titles, your data is incorrectly plotted, your sample calculations are not shown, calculation table is missing, you'll get a 2. Calculation tables have proper units and labels. Graphs are labeled, have appropriate axes, and axes are correctly lit. Something, I can't read that word. Calculations are correct. That gets you that C level. Above the B level would be the axes have consistent numbers, sample calculations in words or numbers, one or the other. Graph has a basic title. Sample calculation missing units. Remember, your sample calculations. Time, seconds. Seconds. You need to include that thing. And if you have that descriptive title, we'll go over that when we get to graphs. Sample calculation in words and numbers and with units. So make any comments about their thing. Remember, we don't have any graphs today, so you don't have to worry about that. But you're going to say how they did on their calculations. At this point, everyone needs to read the conclusion of the lab that they have. This is where most of the points are. So please read through, let's take about 2 minutes and read through the lab report that you have. Okay, so the conclusion is a paragraph. A paragraph says up here, much form detail as possible. Cursory glance, some of you are real detailed, some of you not so much. First of all, it should be the problem. First sentence should be the problem. Either you can just copy down the problem you were given, which is fine, or you rewrite it as a statement. That's fine too. But the first sentence of your conclusion should be the problem. Explain your results. Detailed narrative. In other words, but you want that quantitative data in there. Remember, if you see the word like Q-U-A-N-T, quantitative data, that's what I'm looking for. That quantitative support. The numbers should be in there. If you look at the sample that's in this packet, you notice numbers. So you got as the whirligig, wingspan went from this point to this point, the times went from here to here, and talking about what they did, how they fell, how they worked, all that kind of stuff on that. So you want to be as detailed as possible. This is going to be a nice big chunk of the lab report if you're having all that detail in there. There's about 7 or 8 things, so each one should at least get a sentence. This one question should have 3, 4, 5, depending on how much you need. There's graphs. You talk about the shape of the graphs, all the graphs that you may have to do. Sometimes you do have to do a couple of graphs. You have to compare them. You have to talk about both graphs and things like that. Was the hypothesis right or wrong? Or the third option would be inconclusive. We'll talk about that in a second. Both right or wrong. Why? Again, that specific results. The hypothesis stated that long-wing whirligigs would fall faster. This was false. As evidence, the short ones took an average of 1 second to fall. Long ones took 2 seconds to fall. So again, you're using that quantitative information from the lab in the lab report. Now, inconclusive, sometimes we do a lab and you just can't come up with any type of conclusion because the data is kind of all over the place. That happens. Okay? So you might have a term of inconclusive, in which case your further study would be to redo the lab on that. I'll sit up, please. Errors. Now, you have to state the errors. To get more credit, you're going to explain how they affect the lab. And that kind of comes from those bullet statements as you went along, the different things going out at angles, having to change timers, things like that. Concept. We really didn't do a concept here. Now, most labs have an underlying concept to them. The actual concept here is something we don't actually do in this particular course. It's in an area called fluid. It would be Bernoulli's principle, why how things fly on that. But most of them, there'd be a concept. How is your concept of whatever? Say we're doing a lab about, our next lab is going to be about distance and time. So how is the relationship of distance and time changed, enhanced, reinforced, whatever, by that. Just a one sentence thing. A follow-up lab. What could we study next? What could be the next thing to go from this point? You don't have to explain it, you just have to state what would be the next one. And that daily, how does this apply to daily life? And we look at whirligigs, what device do they remind you of? What? Helicopters. Yeah, in fact, this is how helicopters deal with it, with an engine casualty. And there are seeds that actually use this method. That's how they disperse the seeds. They actually fly away from the tree. But helicopters, if you had if they had an engine failure, they do what's called auto rotation down. In other words, as the helicopter is going down, the air going through the blades will cause them to spin and will give them some lift. So when they hit the ground, it's like a controlled crash. I won't say you get a soft landing, but you don't just kind of smack in the ground. So it's the same thing. Also, early helicopter-like airplanes. There's a thing called autogyro. They still make little ones, but they used to see these more. Basically, it looks like a little airplane with stubby wings. And they have what looks like a helicopter blade on the top, but it's not powered. And as the plane would go forward, basically the air going past that blade would cause it to spin and would give it lift that way. So they're called autogyros. But they had the top blade actually had no engine. It was done just strictly by the air flowing through it to give it lift on that. So, and that's it. So when we look at the rubric, again, this is 3 times, so it'd be 0, 3, 6, 9, 12. Sea level, minimum requirements. Restate the problem, describe the results, how does the data support and reject the hypothesis, state the resource to error, and answer any analysis questions. If you have less detail, notice if I miss 2 of those elements, this goes down. 4 more of those elements, so these are the elements. I add more details, my grade goes up. If I add the quantitative data, that meaningful study and day-to-day connections, that goes up. If I add still more, an explanation of the errors. Here it's just state the errors, here explain the errors. And also the concept. So see, adding data gives you a better score, leaving out information. So remember, detail. The rubric is graded on detail. Again, I said before, you might say, well, why did I get a C? What did I do wrong? And you did nothing wrong. You just did not give me more than a C's worth of detail. There's a couple places on the calculations. Yes, you do your calculations wrong. They're wrong. The graph could be wrong. But then again, whatever you got in your calculations, you use that to answer that, you're not going to lose points because you messed up the calculation and the conclusion. Okay, as long as you use, you want to use your results. What did your results say on all this? Okay? So, what you're going to do is you're going to get back your report. So make some comments on the conclusion for the person you have. Give it back to them. Now hold on. Just say, what you are going to do is you are now going to rewrite this lab. You need the full lab. You have plenty of time. This has been way before. All the things. So the problem, hypothesis, observations, calculations, proper sample, and that detailed conclusion. You're writing a better lab report. Now this one, see the first one you just got basically 10 out of 10 presented. This one I'm going to grade with the rubric. So the first one goes in your packet. You keep that one. That's going to go in your packet. You have that. The one you're going to write at the end, you're going to put over into the box. Okay, so use your resources. Use your old lab. Use your yellow sheets. Use your other things. Remember the conclusion, your own work. Your own work. If you missed something, need some of the calculations, it's okay to talk to people in your group about that part. Remember, the conclusion is your work. It's only your work. Are there any questions? Yes, sir.
Where do we put the score?
Which score?
Reserve control.
Oh, you don't worry about that. That's me. That's what I put on. I'm just showing that's what those are worth. You don't have to worry about scoring. And remember, the one that you have now, that one with the stamp on it, goes into your homework packet. All right? That's the one that goes in your homework packet. That's one of the 2 things in the homework packet. All right? So make sure it gets there. I don't want that one back. It's the homework packet. I want the new one you're going to write. All right? So let's get to work, please. Yes, sir. Well, I would see if there's anything in that. Almost no one writes a 12 on the first go around. They may think they got a 12 on the first go around, but generally, they get very surprised when I get it. But there's always something you could add. Yeah, just let me shut off.